cars can be very handy in people's everyday lives. They allow for busy drivers to instead be more of a passenger during their commute and accomplish tasks that are difficult to do while driving. One of the great things about driverless cars is their ability to react to road conditions and their environment in much the same ways an actual driver would. For example, the car would know to increase its speed when going up a hill and decrease its speed when going down a hill, much like drivers instinctively know to do already. In order for this to be possible, a feedback control system must be put into place to control how the car reacts when a disturbance, such as hills or the wind, enters into the system. For our project, we are proposing a feedback control system that regulates the speed of a car as it comes into contact with different disturbances, maintaining a safe speed and proper disturbance rejection.
The input of our system is going to be the car's set velocity as it pertains to speed limit. And the output of our system is the car's velocity once it has been adjusted correctly for the disturbance. Our block diagram is modeled to take into account disturbances as well as a PI controller. We chose the mass of our car to be 1,000 kilograms and the B value of the damper to be 50 Newton meters per second. For our open loop system, when we plotted it using a step function on MATLAB, the result was around a 98% error and a rise time of close to 70 seconds. This is nowhere near what we would like it to be, which is why a feedback loop needed to be added to bring the response back to the desired speed.
The car on its own, with no disturbances, is BIBO stable, as you can see from our stability graph. Because our system revolves around the idea of being disturbed by outside forces, a closed loop system will be much more accurate. Once the loop is closed, it will also be necessary to have a reference speed as our input, so that the error can be measured and accounted for using our proportional constant k.
Since it is critical for our system to reach the desired speed in a timely manner without overshoot or error, we chose our parameters to be as followed. We want our rising time to be less than 5 seconds because our model should react quickly. We chose our steady state error to be less than 0.1 miles per hour because we don't want variance in the actual versus set velocity for our car. Finally, we chose our percent overshoot to be less than 10% because we don't want our speed to completely overshoot the desired value before it becomes steady. In order to meet these specifications, we opted to use a PI controller. We figured that increasing the gain and adding an integral would make our model meet the requirements we set. Using CISO tool, we began setting the parameters we needed and noticed that in order for our percent overshoot to decrease, we had to add a 0 close to our crossover frequency of 0.44. Once this was done, we moved our graph up until the phase margin was greater than 59 degrees. After that, we looked to see that our response to a step graph met all of our requirements and saw that it did. The PI controller that allowed us to do this resulted in a KP value of 425 and a KI value of 50.
Our final design consists of a PI controller leading into our plan as shown on the screen. When the step response for this is plotted using Simulink, we are given this graph. As you can see, our rise time is less than 5 seconds, our percent overshoot is less than 10%, and our steady state error is close to 0, proving that all of our design specifications were met.
Our final phase margin was 81.5 degrees, which is greater than our 59.1 degree specification. Our gain margin was infinite, which is also acceptable. Our time delay allowed is 3.23 seconds as seen on the graph on the screen. The graph depicts the maximum allowable time delay while still remaining stable.